All right, so tonight we're going to continue looking at sets. Yeah, for those that have joined us today, we already started looking at sets, and we looked at some of the questions. We went through some of the tutorial sheet questions, and now I just want to go back and explain properly step by step what sets are, and even what's this, even the things that sets involve. Yeah, so these sets that we're going to be learning, they're just the same as those sets that you learned at high school. They are not very different, except that they are a bit advanced. Yeah, so what you learned at high school is exactly the same thing that we're going to start with, and later on, we are going to advance. All right, so let's quickly begin. All right, so if you have any questions or you want to uh, ask anything about how I conduct the lessons and the tuitions, feel free to contact me using any of these lines on the screen. Okay, so let's quickly begin. All right, so we're going to start first by defining what a set is, which I believe most of you know it. Yeah, so it's just a well-defined collection of distinct objects. Yeah, so its simple definition is the one that you're seeing on the screen right now. Then some examples of sets that I put in the slide are simply just these. Yeah, so we are going to look at different ways of representing sets. So this one that you are seeing here is the one that we call the roster form. We're going to discuss that. Then there's also this one, which is the interval form. This one is also the interval form. We're going to discuss what it means to have these kinds of brackets. If you have, let's say, 1,2, what it means if you have these types of brackets on a set, or you have this type of brackets on a set. So these two sets are not the same. So in these sets, in this set, we don't have 1 and 2, but in this set, we have 1 and 2. I'll come and explain later what that means. So, and then the other thing that we are going to look at under intervals, when we begin to discuss the intervals, we are going to prove that this is an infinite set. Even this one is an infinite set. But when we say 1, 2, this is a finite set because we can count the elements that are here, but we can't count the number of we can't count the elements that are between 1 and 3 if we write it in this way. So if we have this set, this is an infinite set. This is a finite set because this one, we can count the number of elements. We have 1 and 2, but it's impossible. It's practically impossible for you to count the numbers that are between that are in this set. In short, I'm going to explain why when we begin to discuss about intervals. So make sure that you don't miss any of the classes that we're going to be having. All right, so we quickly continue. Let us look at the types of sets. So we have what is known as the null set. So a null set is a set that is sometimes known as an empty set. Yeah, so a null set sometimes is known as an empty set. Yeah, so its representation, sometimes we use these kinds of brackets to show a null set. Sometimes we use a circle which is crossed like that. So we need to know this. So this is just a quick recap of whatever that you already know. And then we are going to be using tutorial questions as examples. So this is how I'm going to be teaching every day. And then, every time we're meeting, and then tutorial sheet questions are going to be used as examples, meaning we're going to be covering both tutorial sheets and discussing what it means, or or discussing the important concept behind those questions. All right, so what is a singleton set? So a singleton set is simply just a set which contains one element. Yeah, sometimes it's also known as a unit set because it only consists of one element. So a singleton set is a set that consists of one element. So if you have a set which only has A inside, this is called a singleton set because it has one element. All right, so let's quickly continue. All right, so we proceed. Okay. So you can also look at, yeah, so this is just an example of a singleton set. All right, so let us see how we can represent sets. So there are basically three ways that we can use to represent sets. Yeah, so there are also other ways in which we can use, I mean, by which we can present sets, but basically we have three. Let me say, we normally use three ways. Yeah, so the first method or the way of representing sets is the descriptive form. So the descriptive form is simply just a way of representing sets using words. Yeah. And then we also have what is known as the set builder form, where you use brackets and then you also either put a mathematical model inside the brackets, or what I'm trying to talk about is this. So descriptive form, this is the types of sets that have been described. So what you are seeing here, these are all sets which have been described in words. Then these same sets have been written in set builder notation, where you involve the brackets, and you can either use you can write a set in descriptive form but in a set builder notation, and it can also be in an interval form. This is an interval but in set builder, and this is also an interval. It's also an interval, but it's also one way in which we can represent sets, but involving a set builder notation as well. All right, so we also have the roster notation. So this is the roster notation. Yeah, so that is an example which I even gave on the definition of the set. There was a roster notation and also an interval form. So an interval form, like I said, for instance, if you have 1, 2, so 1, 2 can also be written as 1 less x less 2. We can write it this way. That's what it means. Yeah, so when you have, for instance, this 0 x 15, we have 0 less x less or equal to 15. This one can also be written in another form, which is the interval notation as 0, 15. But this side we have an open bracket because we only have a less than symbol. Where we have a less or equal to symbol, we put a square bracket like that. So that's the meaning of those brackets, but I'll explain in details when we just begin to discuss interval notations. So it's a topic on its own. We are going to discuss that. We also discuss how we can show or how we can write sets on the number line, how we can present sets on a number line. So don't miss the lesson so that you don't miss out all the questions and all the discussions that we're going to have. All right, let's look at the finite and infinite sets. So when you talk about a finite set is simply just a set that consists of that consists of elements that you can manage to count. And then an infinite set is simply just a set that has elements that you can't count. In short, it has infinite number of elements. So when we talk about, let's say we have set A which has A, B, C, and set B which has 1, 2, 3, 4. So these two sets that I've shown here are finite sets. Why are they finite? Because you can count the number of elements in these sets. So the first element here we have A, the second one B, the third one is C. Same applies to this one. This is also a finite set. It's also a finite set because we can count the number of elements that are in this set. But when we talk about infinite sets, we're talking about sets which are like intervals. For instance, if you have set, let me say C, set C, which is equal to, when you have C, which is open brackets, then you have 2, 5. Then you have this. So this one is this one is an infinite set because you can't count the numbers that are between 2 and 5. Because and one thing that you have to understand is that whenever we're dealing with intervals, we simply talk about, or we're simply dealing with real numbers. So what are real numbers? Real numbers are simply just the addition of rational and irrational numbers. When we add rational and irrational numbers, we put them together. Whatever that we get as the solution is a set of real numbers. So we're going to discuss real numbers in details as well. In short, we're going to discuss rational and irrational numbers. We also have to discuss how we can show that a given expression or a given number is a rational number or not. So we're going to be using contradiction method to prove that. So don't miss out the lessons that we're going to be having. Okay, so let's continue. So this one is an infinite set. Same applies to set D when we write it like this, 1, 3. This is also an infinite set. Then if we say 0 less x less 5, this is also an infinite set. We can't count the number of, if we write it like this, and then we say where x is a member of real numbers, then it becomes an infinite set. But if we say where x is a member of integers, it means that this is a finite set, meaning we are able to count the number of integers between 0 and 5. But if we say x is a member of real numbers, it means that we can't count the number of elements or the number of numbers that are between 0 and 5. So I'm going to explain everything when we begin to look at intervals. And the reason why we can't count the numbers there, I'll explain everything. Okay, so let's quickly continue. So I've talked about the definition of a finite set and an infinite set. So a finite set is a set that has a finite or countable number of elements. And an infinite set is a set that contains an uncountable or infinite number of elements. So let us look at these examples. So I gave examples of A and B, and this is what we have there. So if you look at set A there, set A is considered to be a finite set because you can count the number of elements in the set. Then set B is considered to be an infinite set because of these 3 dots that we have there. These 3 dots are telling us to say the set continues going, it's infinity. It goes up to infinity. So sometimes these dots cannot be put on the right. Sometimes they may be on the left. You can have something like this. Let's say we have set C, which is open brackets, and then you have 1, 2, 3 dots. Then you have maybe 0, and then you have 1, 2. So this is also an infinite set because we have numbers that are moving from the positive. We have numbers moving from 2 to negative infinity. Yeah, so we are going to discuss more about these infinite and about infinite sets when we begin to look at intervals. All right, so let's look at this question from the tutorial sheet. It's talking about stating whether the elements, or rather the sets, are infinite or finite. Okay, so we start with the first one there. So the first one says x is such that x is a member of natural numbers. So all these sets that you are seeing here have been written in set beta notation. Now they're asking us to state whether they are finite or infinite. Okay, they're asking us to determine which set is infinite, meaning there are some which are not infinite. So we look at the first one. So the first one says x is such that x is a member of natural numbers and x is a prime number. So we are looking at natural numbers and prime numbers. So natural numbers are simply just counting numbers starting with 1. So whenever you're counting and you decide to start with 1, it means that you are counting using what? Natural numbers. So these are natural numbers. And then they're saying, and X is a prime number. So from the set of natural numbers, we remove out prime numbers. So we have the first element that we have from the set of natural numbers, we remove out prime numbers. So the elements that we're going to have are, the first prime number that we have is 2, because we know a prime number is simply a number that consists of only 2 factors, 1 and itself. So we have the first prime number is 2. The second prime number that we are going to have is 3. Then we have 5. Then we have 7. So there are a lot of prime numbers. You can't manage to count them. So since we have these 3 dots at the end, this implies that the first set there is what? Is infinite. Let's look at the second part. So the other one is X, which is this one. So the other set that we are trying to inspect here is this one, the second one. Let us try to check if this is an infinite set. So they're saying X is such that X is a quadrilateral on a plane. A quadrilateral on a plane. So you need first to understand what is a quadrilateral. So a quadrilateral is simply just an object. It's simply just an object, or a shape rather, or a polygon in short. Let me say a polygon which has 4 sides. Quadrilateral is simply just a polygon which has 4 sides. And then they're saying X is such that X is a quadrilateral on a plane. So this one is also infinite in the sense that it's very easy for you to make or to come up with quadrilaterals on a plane. I don't know how I can explain this one. Okay, if there's a way I can explain it in pictorial or while writing, it would have been easy. Okay, let's try to look at this one first. I'll get back to this one if I think of the best way to explain it so that you understand. Okay, so we have the third part there, which is X is such that X is a member of natural numbers, and X is, and then X squared. Okay, let me do this. And then we have X squared. Let me use white so that you see. So, and then we have X squared minus 25 is less or equal to 0. So that is also a finite set. I mean, this one is a finite set. It's not an infinite set. Oh, let's first try to check the solution. That's when we conclude. But because it's an interval, then we can say it's an infinite set, not a finite set rather. Yeah, so this is an interval. The solutions that we're going to get them in interval form. So we don't expect this to be an infinite set because of this same symbol here. Because whenever you have this symbol, it means that the solution that you are going to have is going to be a range. It's not going to be 1 or 2 solutions. No, it's going to be a range. So if you want me to solve this one, we can solve it and prove that it's a finite set. It's not an infinite set. Rather, it's an infinite set. It's not a finite set. Yeah. So this one is an infinite, and the reason is because it's an interval. Whenever you're dealing with greater than or less than symbol, it means that the solution that you're going to have is going to be an interval. And whenever you have an interval as the solution, you expect that set to be an infinite, because you can't count the number of elements that are in an interval. Because in most cases, okay, let's look at the question first before we can begin, before I say anything. They are saying X is a member of natural numbers, and then we have X squared minus 25. Yeah, so this one is not an infinite, it's a finite set because we're dealing with natural numbers. I thought we're dealing with real numbers. I was looking at this one. Okay, so we're saying X is such that X is a member of natural numbers, not real numbers. So when you're dealing with an interval and you have real numbers there as the value of X, it means that that given set is what? Is an infinite set. So whenever you're dealing with real numbers and then you have an interval this side, means that that is an infinite set. And the reason why it's an infinite, I'll explain. And then we have this one I'm saying it's a finite set. This one is a finite set. Okay, let's try to solve this one first. We see what we're going to get. Okay, so if we solve, if we were to solve this one, then we'll get something like this. So we're going to have x minus x squared minus 5 squared being less or equal to 0. Then this will be a difference of 2 squares. So meaning we have x plus 5 and x minus 5 being less or equal to 0. Then if you equate x plus 5 and x minus 5 to 0, you're going to get your critical points as -5 and +5. So after getting your critical points, you can put them on the number line there so that you can test them. So you have -5 and you have 5 there. So we get this side, we know that all the values that are this side are less than what? Are less than or equal to -5. And the values between -5 and 5, we write them as x less or equal to, we write them as -5 less or equal to x less or equal to 5. Then this side, we have all the values that are greater than or equal to 5. So we can test the points. So if we get any number that is less than -5, any value that is less than -5, we can get -6. We try -6, we put -6 there, and then we say +5. The answer that we're going to get to be -6 plus 5 there will give us what? -1. So we expect to have negative there. And then when we put -6 there, we're going to have -6 minus 5, that will be -11. So we'll still have another negative. So when we multiply negative and negative there, negative times negative, we're going to get a positive. So we check this region. We ask ourselves to say, is a positive less than 0? Is a positive less than 0? The answer is no. So meaning this region is denied. I mean, this region is not part of our solution. So in most cases, though not always, in most cases, when this region is not part of your solution, automatically even this region is not part of your solution. It means that your solution is the middle part. So this is our solution in between. If you want, or if you want on your spare time, you can test it, or let's test it so that you prove. Let me just do it quickly. So we can get any value that, any number that is between -5 and 5. We can even get a 0. So when you put a 0 where there's x there, and then we say 0 plus 5, the answer that we're going to get is what? +5. So we can just write a positive. Then we put a 0 there, 0 minus 5, the answer will be negative. So we have -5, so I'll just write a negative. So positive times negative, the answer is negative. So is a negative number less than 0? If the answer is yes, then this region is part of our solution because it's making this statement true. Okay, so this is our solution in between. So now, the other way you can write this question that we've been given there is that x is such that x is a member of what? Of natural numbers. And then negative, the natural numbers between negative less or equal to, -5 less or equal to x, which is less or equal to 5. So this is the reason why I said this is a finite set, because when you talk about natural numbers from -5 to 5, these are, let me write it here. So we have -5 itself because we have less or equal to there. Sorry, -5 is not part of the natural numbers. We start from 1. So the natural numbers between -5 and 5, we start from 1, and then we move on to 2, and then we have 3, we have 4, and we have 5. So these are the natural numbers that we have for this set. And this is a finite set because we are able to count the number of elements in this set. We have 1, 2, 3, 4, 5. Okay, so this one, I said it's an infinite set. This one, I said it's an infinite set because we are dealing with real numbers and the interval here, and we have an interval there. So if we talk about real numbers, we're simply combining rational and irrational numbers. So when you talk about rational numbers are simply numbers that can be expressed in the form x over y. This is a fraction form. So any rational number can be expressed in the form of a fraction. And then this is rational. And then for irrational numbers, irrational numbers, these are numbers that can't be expressed in the fraction form, like pi. You can't express pi in the fraction form. And then apart from that, we have a lot of irrational numbers like the root of 2, the root of 3, the root of 5. You can't express these as fractions. As a result, they are known as irrational numbers. So when you add the set of rational numbers and irrational numbers, you come up with a set that is known as the set of real numbers. So when we talk about the numbers that are between 0 and 5, this is what this statement says. So when you talk about the numbers that are between, the real numbers that are between 0 and 5, it means that we're also including the square roots of 2, the square root of 3, because we know that the square root of 2 will give you something like 1.4 something going up. It will be in decimals, of course, meaning it's also between 0 and 5. So if we talk about those numbers, we are also talking about 0.00000000001. It's also part of this set. Now, when we say let's count the numbers that are in between, we can't manage to count them. Hence, we say it's an infinite set. And then when we talk about this other set here, it says x is such that x is a member of natural numbers where x is a multiple of 3. So natural numbers that are multiples of 3, we can also say it's infinite because we don't have an ending. They have not specified whether even 99 is part of this set, or we are just supposed to end at 100, or we're just supposed to end at 1000. If we have an ending, then we would have said it's a finite set, but this one is an infinite set because it's open. In short, it's open. It's just saying natural numbers that are multiples of 3. And hence, we are talking about numbers that we can't manage to count, because if I want, I can write 9, I can write a lot of 9s up to Lusaka. I'm just writing 9s. These are multiples of 3. 3 can go into this number. So I'm sure you know why I'm saying this set is also infinite. Okay, we look at this set. X is such that X is a house. X is a house in America. Do you think it's possible for you to count all the houses in America? If the answer is no, then this is also an infinite set. Then we look at the last part here, which is X is such that X is a factor of 2100. Do you think we can manage to count the factors of 2100? If the answer is yes, then this is a finite set. All right, so let's try to check if we have another question. Okay. I thought I had also included another question about finite and infinite. All right, so I think there's another question, though not on finite and infinite. Do we have any questions about finite and infinite sets before we can proceed to the other section we are supposed to discuss tonight? Do you have questions? So if you have a question, you can just unmute yourself and ask. All right, so silence means there's no question. All right, so as we can see, it's it's already counting down. So the link, the session might end anytime from now. So what I'm going to do is that I'm going to end the session. I'm going to end the session right now. And I want you to join using the same link which I sent in the group. I want you to join so that we finish up this slide. So let's quickly leave the meeting and then join using the same link. So let's quickly join using the same link.